We take 2NH3 give rise to N2 plus 3H2. Okay. So here the rate is independent of the concentration. So it is not going to depend upon the concentration of the reactant. Okay. So ಆಗ ನಾವು R is equal to ಬರೆದ್ರೆ K into concentration of reactant. So it is independent of the zero. So that is going to be zero order reaction. Okay. Similarly, we can also take this reaction in the presence of sunlight. So R is equal to H2 CO2. So that is also independent of the concentration of the reaction. So your zero order reaction example ಆಗುತ್ತೆ. Okay. So here in this case, in the examples you can see there H2 plus Cl2. So at high pressure, the solid catalyst surface is absorbed or adsorbed with the gaseous reacting molecule. The rate remains constant here. So rate, when the rate remains constant, and it is going to become independent of concentration. So ಯಾವಾಗ rate ನಮಗೆ constant ಆಗುತ್ತೆ ಯಾವಾಗ ಅದು ಏನಾಗುತ್ತೆ independent ಆಗಿಬಿಡುತ್ತೆ. So that time that reaction is going to be said to be zero order reaction. Okay. So that is about zero order reaction. So next ನಮಗಿರೋದು unit of rate constant. Unit of rate constant. Okay. Of rate constant. So already we know that rate of the reaction is always going to be concentration and time. Concentration and time inverse. So this is what rate is going to be, and is independent of order of reaction. Okay. So therefore we have a formula that K is equal to mole liter inverse 1 minus n second inverse. Okay. So where n will be order of the reaction. Okay. So therefore when n is 0, 1 minus 0. So it will be 1. So for 0 order, it will be mole liter inverse second inverse. Okay. Then for first order is 1 minus 1 is 0. So anything over 0 is 1. So therefore it will be second inverse for first. And for second, it is going to be minus 1. So therefore it will be mole inverse liter second inverse. So these are the units of zero order reaction, first order reaction, and second order reaction. So these are all the units of K, that is rate constant. Okay. So K when is in the first order, K when is in the zero order, Kn is in the second order. So at that time there is going to be the value of K, that is rate constant. Okay. So then after that, next we have is molecularity of a reaction. Is very important. Molecularity of a reaction. Okay. So in this, there will be two types. One is elementary reaction, and one more is complex reaction. Elementary reaction, complex reaction. So here elementary reaction. What do you mean by elementary reaction? Andre? These elementary reactions which takes place in only one step. So these are the reactions which takes place at only one step, in which reactants are directly converted into products. In which reactants are directly converted to products. So they are said to be elementary reactions which happens in only one step. Okay, so for example, if you take H2 plus I2, you raise to 2HI. So one step reaction. Okay. So theoretically and experimentally, the rate equation are going to be same here. The rate equation remains the same. And for complex reaction, it is going to be taking place in a sequence of elementary series or elementary reaction. In a sequence of elementary reaction. Okay, so complex reaction takes place in the sequence of elementary reaction to give products. Okay, to give products. So one of the elementary reaction that takes place very slowly. So adana ನಾವು slow step ಅಂತ ಕರಿತೀವಿ. ನಾನು ಆಲ್ರೆಡಿ ಹೇಳಿದ್ದೆ ಇದ್ರ ಬಗ್ಗೆ. So series of elementary reactions ಆಗುತ್ತೆ. ಎಲಿಮೆಂಟರಿ ರಿಯಾಕ್ಷನ್ ಅಂದ್ರೆ ಅದು ಒಂದೇ ಸ್ಟೆಪ್ ಅಲ್ಲಿ ಆಗುವಂತದ್ದು. ಕಾಂಪ್ಲೆಕ್ಸ್ ರಿಯಾಕ್ಷನ್ ಆಗುತ್ತೆ ಆ ತರ ಒಂದ್ ಸ್ಟೆಪ್ ತುಂಬಾ ಇರುತ್ತೆ. ಅದನ್ನ ಸೀರೀಸ್ ಸೀಕ್ವೆನ್ಸ್ ಆಫ್ ಎಲಿಮೆಂಟರಿ ರಿಯಾಕ್ಷನ್ಸ್ ಅಂತ ಹೇಳ್ತೀವಿ. ಅದರಲ್ಲಿ ಒಂದು ಏನ್ ಬರುತ್ತೆ ನಮ್ಗೆ ಸ್ಲೋ ಸ್ಟೆಪ್ ಕೂಡ ಬರುತ್ತೆ. ಅದು ಕಾಂಪ್ಲೆಕ್ಸ್ ರಿಯಾಕ್ಷನ್ ರೇಟ್ ಹೇಳುತ್ತೆ ಅಥವಾ ರೇಟ್ ಆಫ್ ಕಾಂಪ್ಲೆಕ್ಸ್ ರಿಯಾಕ್ಷನ್ ದಟ್ ವಿಲ್ ಪ್ರೆಡಿಕ್ಟ್. ಓಕೆ, ಸೊ ಇದನ್ನ ನಾವು ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕಂದಾಗ, ಸೊ ಈಗ ಒಂದು 3 ಸೆಕ್ಷನ್ ಕ್ಲಾಸ್ ರೂಮ್ ಇದೆ ಅಂದ್ರೆ 3 ಸೆಕ್ಷನ್ ಕ್ಲಾಸ್ಗೆ ಡಿಫ್ರೆಂಟ್ ಟಾಪಿಕ್ಸ್ ಮಾಡಿರ್ತೀವಿ ಅಥವಾ ಒಂದೇ ಟಾಪಿಕ್ ಮಾಡಿರ್ತೀವಿ. ಬಟ್ ಯಾರಿಗೆ ತುಂಬಾ ಕಮ್ಮಿ ಟಾಪಿಕ್ ಆಗಿರುತ್ತೆ ಅವ್ರದ್ದು ಸಿಲೆಬಸ್ ನ ಎಕ್ಸಾಮ್ ಕೊಟ್ಟಿರ್ತೀವಿ. ಸೊ ಮೇ ಬಿ ಯಾವತ್ತೋ ಅವ್ರಿಗೆ ಇರೋ ದಿನ ರಜೆ ಇರ್ಬೋದು ಅಥವಾ ಏನಾದ್ರು ಬಂದು ಅವ್ರಿಗೆ ಸಿಲೆಬಸ್ ಕಮ್ಮಿ ಆಗಿದ್ರೆ ಆ ಕ್ಲಾಸ್ಗೆ ಏನ್ ಇದಾಗಿತ್ತು ಅದನ್ನ ನಾವು ಎಕ್ಸಾಮ್ ಕೊಡ್ತೀವಿ. ಅದೇ ರೀತಿ ಇಲ್ಲಿ ಕಾಂಪ್ಲೆಕ್ಸ್ ರಿಯಾಕ್ಷನ್ ಅಲ್ಲಿ ಸುಮಾರು ಸ್ಟೆಪ್ಸ್ ಆದ್ರೂ ಯಾವ್ದು ಸ್ಲೋ ಸ್ಟೆಪ್ ಇರುತ್ತೆ ಅದನ್ನ ರೇಟ್ ಆಫ್ ರಿಯಾಕ್ಷನ್ ಕಂಡುಹಿಡಿಯೋದಕ್ಕೆ ಇಲ್ಲಿ ತಗೊಂತಾರೆ. ಸೊ ಅದನ್ನ ನಾನು ಹೇಳಿದ ರೇಟ್ ಕಂಡುಹಿಡಿಯೋಕೆ ಅದು ಯೂಸ್ ಮಾಡ್ತಾರೆ. ಓಕೆ, ಸೊ ಈಗ ಈ ಎಲ್ಲಿ ಕಾಂಪ್ಲೆಕ್ಸ್ ರಿಯಾಕ್ಷನ್ ಗೆ ನಾವು ಡಿಕಂಪೋಸಿಷನ್ ಆಫ್ ಹೈಡ್ರೋಜನ್ ಪೆರಾಕ್ಸೈಡ್ ಎಕ್ಸಾಂಪಲ್ ತಗೊಬಹುದು. ಸೊ ಫಸ್ಟ್ ಇಲ್ಲಿ 2H2O2 in the presence of alkaline medium, that is 2H2O plus O2. Okay, so rate is equal to H2O2 ಮತ್ತೆ I minus. ಸೊ ಇದು ಎರಡು ಸ್ಟೆಪ್ ಅಲ್ಲಿ ಆಗುತ್ತೆ. ಸೊ ಫಸ್ಟ್ ಸ್ಟೆಪ್ ಏನು, H2O2 plus I minus U raised to H2O plus IO minus. ಮತ್ತೆ ಸೆಕೆಂಡ್ ಸ್ಟೆಪ್ ಇದೆ, ಅದರಲ್ಲಿ H2O2 plus I minus U raised to H2O plus I minus plus O2. ಸೊ ಇದರಲ್ಲಿ ಈ ಸ್ಟೆಪ್ ಸ್ಲೋ ಸ್ಟೆಪ್ and this will be fast step. ಸೊ ಇಲ್ಲಿ ನೀವು ಎರಡನ್ನ ಸೊ ಇಲ್ಲಿ ಎರಡನ್ನು ನೀವು ಈಕ್ವೇಟ್ ಮಾಡಿದಾಗ ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ ಐಒ ಮೈನಸ್ ಮತ್ತೆ ಐಒ ಮೈನಸ್ ಕ್ಯಾನ್ಸಲ್ ಆಗುತ್ತೆ. ಸೊ ನಮಗೆ ಅಬೌವ್ ರಿಯಾಕ್ಷನ್, ಸೊ ವಿಲ್ ಗೆಟ್ ದಿಸ್ ರಿಯಾಕ್ಷನ್. So that is slow step and fast step. So slow step ಇಂದ ಏನಾಗುತ್ತೆ ನಮಗೆ rate ಸಿಗುತ್ತೆ. The rate equation agrees with the theoretical and experimental rate equation. Okay, so this is a theoretical ಆದ್ರೆ experimental ನೋಡಿ ಇಲ್ಲಿಗೆ ಬರಿಬೇಕು ನಾವು ಈ equation ಬರೆಯೋದಾದ್ರೆ rate is equal to k into H2O2 ಮತ್ತೆ I minus. ಸೊ ಈ ಒಂದು ಜನರಲ್ ಈಕ್ವೇಶನ್ ಐ ಮೈನಸ್ ಯಾಕೆ ಬಂತು ಅಂತ ನಮಗೆ ಈ ಸ್ಟೆಪ್ ವೈಸ್ ರಿಯಾಕ್ಷನ್ ಇಂದ ಗೊತ್ತಾಗುತ್ತೆ. ಓಕೆ, ಸೊ ಹಾಗಾಗಿ ಇದು ಎರಡು ಸ್ಟೆಪ್ ಮಾಡೋದಕ್ಕೆ ದೇ ಯೂಸ್ ಆಲ್ಫಾ ಅಂಡ್ ಮೀಡಿಯಂ. ಓಕೆ, ಸೊ ಇದನ್ನ ನಾವೇಂತ ಕರಿತೀವಿ, ಕಾಂಪ್ಲೆಕ್ಸ್ ರಿಯಾಕ್ಷನ್ಸ್ ಅಂತ ಕರಿತೀವಿ. ಓಕೆ, ಸೊ ನಮ್ಗೆ ಎರಡು ರೀತಿಯಾದ ರಿಯಾಕ್ಷನ್, ಒಂದು ಎಲಿಮೆಂಟರಿ ಮತ್ತು ಇನ್ನೊಂದು ಕಾಂಪ್ಲೆಕ್ಸ್. ಸೊ ನೆಕ್ಸ್ಟ್ ವಿಲ್ ಟೇಕ್ ಒನ್ ಮೋರ್ ಎಕ್ಸಾಂಪಲ್ ಹಿಯರ್. We can take 2N2O5 give rise to 4NO2 plus O2. So therefore R is equal to N2O5. Okay. Then two step ಅಲ್ಲಿ ಆಗೋದಿದು ಫಸ್ಟ್ ಟೈಮ್ N2O5 ಡಿಕಂಪೋಸ್ ಆಗುತ್ತೆ NO2 ಮತ್ತೆ NO3 ಆಗಿ, which is a slow step. Then N2O5 reacts with NO3 gives 3NO2 plus O2, which is faster. So if we equate these two, we get sum ಮಾಡಿದ್ರೆ ಎರಡು ಬರುತ್ತೆ. 2N2O5 gives to 4NO2 plus O2. Okay, so this is going to be the complex reaction which takes place in a two-step reaction ಆಗುತ್ತೆ. Okay, that's clear. Okay. So after seeing this, how we can define molecularity of a reaction? So molecularity of a reaction is defined as number of reacting species. Number of reacting species taking part in an elementary. Okay, reacting species taking part in an elementary reaction. Elementary reaction. Okay. So the number of reacting species which is taken part in elementary reaction. So that's now molecular of the reaction. For example, if we have NH4 NO2 give rise to N2 plus 2H2O. So ಇಲ್ಲಿ ನೋಡಿದ ತಕ್ಷಣ ನಮಗೆ reacting species ಎಷ್ಟಿದೆ, only one ಇದೆ. So ಹಾಗಾಗಿ this will be unimolecular. This is going to be unimolecular. ಅಂದ್ರೆ ಮಾಲಿಕ್ಯುಲಾರಿಟಿ ಕೇಳಿದ್ರೆ ಇಲ್ಲಿ ನೀವು ಇದಕ್ಕೆ ಮಾಲಿಕ್ಯುಲಾರಿಟಿ ಎಷ್ಟು ಅಂದ್ರೆ can say molecularity is going to be equal to 1. Okay. So ಅದೇ ರೀತಿ if we take this one, so ಇಲ್ಲಿ ಮಾಲಿಕ್ಯುಲಾರಿಟಿ ಏನಾಗುತ್ತೆ 2 ಆಗುತ್ತೆ. It is going to be bimolecular. So it is bimolecular. So ಹಾಗಾಗಿ ಅದು ಹೋಗುತ್ತೆ. ನೆಕ್ಸ್ಟ್ ಆಗಿ ಅದು ಸೊ ನೀವು ರಿಯಾಕ್ಟಿಂಗ್ ಸ್ಪೀಸೀಸ್ ಎಷ್ಟಿದೆ ಕೌಂಟ್ ತಗೋಬೇಕು, ಇನ್ಕ್ಲೂಡಿಂಗ್ ಸ್ಟಾಯ್ಕಿಯೋಮೆಟ್ರಿಕ್ ಕೋಎಫಿಷಿಯಂಟ್. ಸೊ ಅದನ್ನು ಮತ್ತೆ ರಿಯಾಕ್ಟಿಂಗ್ ಸ್ಪೀಸೀಸ್ ಎಷ್ಟಿದೆ ಅಷ್ಟನ್ನು ಆಡ್ ಮಾಡ್ಕೊಬೇಕು. ಓಕೆ. So actually the probability of more than 3 reacting species colliding simultaneously is very small. ಆ ಒಂದು probability ತುಂಬಾ ಕಮ್ಮಿ ಇರುತ್ತೆ. 3 reacting species ಇರುವಂತಹ ರಿಯಾಕ್ಷನ್ ಅಲ್ಲಿ ಕೊಲೈಡ್ ಆಗುವಂತದ್ದು it will be very less. Okay, so adrinda molecularity greater than 3 is not observed. Okay, so therefore reaction involving more than 3 molecules in the balanced equation must be complex and must take place in more than one step. Okay, so ಜಾಸ್ತಿ ಮೂರಕ್ಕಿಂತ ಜಾಸ್ತಿ ಬರ್ತಂದ್ರೆ it has to take place in several steps. ತುಂಬಾ ಸ್ಟೆಪ್ಸ್ ಅಲ್ಲಿ ರಿಯಾಕ್ಷನ್ ಆಗಬೇಕಾಗುತ್ತೆ. So but molecularity cannot be greater than 3, which is not usually observed. Okay, so next we have to find the difference between order of the reaction and molecularity of the reaction. Okay, so order of the reaction and molecularity difference ಹೇಳ್ಬೇಕು ಎರಡರ ಮಧ್ಯ. So order of the reaction is definition ನೀವು ಬರೀಬಹುದು, sum of powers ಮಾಡಿದ್ರೆ ನಿಮಗೆ order of the reaction ಸಿಗುತ್ತೆ. ಅದೇ ರೀತಿ ಇಲ್ಲಿ number of reacting species, the definitions you can note here. Number of reacting species. Okay, next ಅದಾದ್ಮೇಲೆ order of reaction ಇಲ್ಲಿ whole number 0 fraction ಇರಬಹುದು ಅಂತ ಹೇಳಿದೆ, ಬಟ್ ಅದು ಮಾಲಿಕ್ಯುಲಾರಿಟಿ ಪಾಸಿಬಲ್ ಇಲ್ಲ. ಮಾಲಿಕ್ಯುಲಾರಿಟಿ ಆಲ್ವೇಸ್ whole number ಆಮೇಲೆ 0 ಆಗೋದೇ ಇಲ್ಲ. It is always whole number and it cannot be 0. Okay, so molecularity cannot be 0, always whole number. Order is experimental quantity, is experimental. Okay, but elementary ಇದು molecularity ಏನಾಗಿರ್ತದೆ always theoretical. Okay, so like this these are the differences between order of the reaction and molecularity of the reaction. Okay, so very ತುಂಬಾ important order of the reaction ಮತ್ತೆ molecularity of the reaction ಮಧ್ಯ differences ಗೊತ್ತಿರಬೇಕು. Okay, so next what we have is integrated rate equation. Integrated rate equation. So next ನಮಗೆ so ಏನಿದೆ integrated rate equation, why we need this integrated rate equation? Okay, so ನಾವು ಆಲ್ರೆಡಿ instantaneous rate ಬಗ್ಗೆ ಓದಿದ್ವಿ. instantaneous rate ಅಂತ So that instantaneous rate which is obtained by the slope of the tangent at instant in concentration versus time graph, which is not convenient and lacks accuracy quite often. So ಆ ಮೆಥಡ್ ಏನು ನಾವು ಸ್ಲೋಪ್ಸ್ ಡೈರೆಕ್ಟ್ ಆಗಿ ತಗೊಂಡು ಆನ್ಸರ್ ಅಂತ ತಗೊಂಡಿದ್ವಿ. ಸೊ ಅದು ನಾಟ್ ಕನ್ವೀನಿಯಂಟ್ ಅಂಡ್ ಲ್ಯಾಕ್ಸ್ ವೆರಿ ಆಫನ್. ಸೊ ಅದನ್ನ ಡಿಫಿಕಲ್ಟ್ ಆಗಿರೋದ್ರಿಂದ ಏನ್ ಮಾಡ್ತಾರೆ ಇಲ್ಲಿ, ಟು ಅವಾಯ್ಡ್ ದಟ್ ಆ ಡಿಫರೆನ್ಷಿಯಲ್ ಈಕ್ವೇಶನ್ ಏನಿತ್ತು ನಾವು ಇನ್ಸ್ಟಂಟೇನಿಯಸ್ ಅಂದಾಗ ನಮಗೆ ಡಿ ಆರ್ ಬೈ ಡಿ ಟಿ ತಗೋತೀವಿ ಅದು. ಆ ಡಿಫರೆನ್ಷಿಯಲ್ ಈಕ್ವೇಶನ್ ನೌ ದೇ ಆರ್ ಗೋಯಿಂಗ್ ಟು ಇಂಟಿಗ್ರೇಟ್. Okay, so that they'll get the rate equation to avoid that inconvenience regarded during instantaneous rate. Okay, so for that they use integrated rate equation. So here for integrated rate equation for zero order, if we take first we have is for zero order reaction. Okay. So here to consider a zero order reaction. So zero order again we have to consider a zero order reaction in which R gives product P. So R is the reactant. Okay, so this is concentration of reactant at time T. So this is the concentration of reactant at time T. Therefore rate of reaction R is equal to minus d of R by dt. So this we know to write. So equation 1. Then according to law of mass action R is equal to K into zero order andre it will be like this. So 1 and 2 na equate ಮಾಡಿದ್ರೆ R by same ಬರೋದ್ರಿಂದ minus d of R by dt is equal to K into R to the power of 0. So R to the power of 0 andre adu 1 ಆಗುತ್ತೆ. Okay, so I simply change it into K. Okay, so next ಏನಾಗುತ್ತೆ, this dt goes here, so that dt goes there, then it will become minus dr by dr is equal to K into dt. So this is what we will get. Okay, so we can take this reaction as 3. So integrating equation 3 on both sides, so minus d of R is equal to K into integration of dt. Okay, so here on integrating this we'll get minus of R is equal to K into T plus I, where I is the integration constant. I is integration constant. Therefore R is equal to minus minus KT plus I. Okay, since it is a zero order reaction at time T is equal to 0. Okay, so therefore if you put T0 here, what you will get? You will get R is equal to I. Therefore this is at R0, since it is 0, R0 is equal to I. Okay, substitute ಮಾಡಬಹುದು ಇದನ್ನು ನಾವು I ಜಾಗದಲ್ಲಿ. that is R is equal to minus KT plus R naught. Plus R naught. Instead of I, you can put R naught. So KT akade hogre plus agutte. Therefore R plus KT is equal to R naught. Okay. So keep KT there only and send R naught here. So R naught minus R minus R. Therefore keeping K there, you need a rate constant is equal to, therefore K is equal to R naught minus R whole thing divided by T. Whole thing divided by T. So this is going to be the derivation or important derivation for zero order reaction, that is K is equal to R naught minus R by T. So this is very important. Okay. So note down ಮಾಡ್ಕೊಳ್ಳಿ, ತುಂಬಾ important. This has been repeated many times. Make a note of this. Okay. So after this, let's take the equation. So I'll just clear this part. Here we take equation R. So taking this equation and comparing this equation with the y is equal to mx plus c. Okay. So ಇದನ್ನ equation ತಗೊಂಡು ಇದನ್ನ graph compare ಮಾಡೋದು y is equal to mx plus c ಗೆ. So graph R versus time, that is concentration versus time graph. Okay. So here the concentration versus time graph R versus T. Okay. So here the intercept C is going to be R naught. Okay. And slope is minus K. You can see here slope is minus K. So I can write like this. And here K will be equal to minus slope. Okay. So K will be equal to minus slope. So here for zero order reaction for in integrated rate equation, the graph plot of R versus T is used a straight line with the slope minus K. Okay, the slope minus K. It is written as K is equal to minus slope. Either of the ways fine, not a problem. Okay. So ಇದು ನಮಗೆ zero order ಗೆ ಆಯ್ತು. So ಇದು ಗೊತ್ತಾಗಿದೆಲ್ಲ zero order ಗೆ. So zero order ಆದ್ಮೇಲೆ ನೆಕ್ಸ್ಟ್ ನಮಗಿರೋದು ಇಂಟಿಗ್ರೇಟೆಡ್ ರೇಟ್ ಈಕ್ವೇಶನ್ ಫಾರ್ ಫಸ್ಟ್ ಆರ್ಡರ್. So integrated equation for first order. Again, also here also we'll consider the equation R is C. Then R is equal to minus d of R by dt. Then R is equal to k of R to the power of 1. So this will remain same. So then if we take minus d of R by dt is equal to k into R. Okay. So dt will shift here to this end. So it will be like this. After that, we have to integrate on both sides. This k of R will come here. So therefore, okay, it will be like this. So now integrating this. Okay, so now integrate modality. So from this, what you'll get is, so here integrating this over this minus ln R is equal to kt plus I.
ಸರ್ ಅಲ್ಲ ಆರ್ ಡ್ಯಾಶ್ ಇದ್ದಿದ್ದು ಆರ್ ಯಾಕಾಯ್ತು?
ಯಾವುದು ಇದಾ?
ಎಸ್ ಸರ್.
ಆರ್ ಡ್ಯಾಶ್ ಅಲ್ಲ, ಇದು ಆರ್ ಟು ದ ಪವರ್ ಆಫ್ 1. ಆರ್ ಟು ದ ಪವರ್ ಆಫ್ 1 ಬರ್ಕೊಂಡ್ರು ಒಂದೇ, ಬರಲಿಲ್ಲ ಅಂದ್ರೆ ಒಂದೇ ತಾನೆ ಅಲ್ವಾ?
ಎಸ್ ಸರ್.
ಇದು ಫಸ್ಟ್ ಆರ್ಡರ್, ಅದಕ್ಕೆ 1 ಅಂತ ಬರೆದಿದ್ದೀನಿ. ನೆಕ್ಸ್ಟ್ ಅದನ್ನ ಬರ್ಕೊಂಡಿಲ್ಲ ಅಷ್ಟೇ, ಬರ್ದಿಲ್ಲ ಅಂದ್ರೆ ಅದಿದೆ ಅಂತ ಅರ್ಥ. ಓಕೆ. ಸೊ ಇಂಟಿಗ್ರೇಷನ್ 1 by r ಮಾಡಿದಾಗ ln r ಬಂತು ಪ್ಲಸ್ kt ಪ್ಲಸ್ I. ಸೊ ಇದೇನಾಗುತ್ತೆ ನೆಕ್ಸ್ಟ್ ln r is equal to minus kt plus I. So next again at time t is equal to 0. t is 0 ಆದ್ರೆ ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ, ln r ಇದು ನಾಟ್ ಆಗುತ್ತೆ, ln r ನಾಟ್ is equal to I. ಸೊ ಮತ್ತೆ ಈ ಜಾಗದಲ್ಲಿ ಹಾಕೋದಾದ್ರೆ ln r to minus kt plus ln r naught. ಓಕೆ. ಸೊ ಈಗ ಇಲ್ಲಿ ಅಗೇನ್ ln r plus kt is equal to ln r naught. So therefore kt is equal to ln r naught minus ln r whole thing divided by ಇದು ಬೇಕಾದ್ರೆ ನಾವು ಇಲ್ಲಿ ಇಷ್ಟಾದ್ಮೇಲೆ ಇದು ಲಾಗರಿಥಮ್ ಫಾರ್ಮುಲಾ ಹಾಕೋದು, kt is equal to ln of r naught by r ಅಂತ ಬರೀಬೇಕು. Okay, so kt is equal to ln r naught by r. So to convert this ln to natural log n ಮಾಡ್ತೀವಿ 2.303 ನ multiply ಮಾಡ್ತೀವಿ. So therefore it will be 2.303 log of r naught by r. Okay. So ಈ ತರ ಪುನಃ t ಇಲ್ಲಿ ನಮಗೆ ಡೌನ್ವರ್ಡ್ ಬರುತ್ತೆ. So therefore k is equal to 2.303 log, so 2.303 log of r naught by r. So this is the final equation. Okay, so that is going to be the final equation. So this is very important. Okay, so this is important. Now again we have to plot a graph for that. So I'll just clear this part. So here, if we take this equation, ln of r equal to minus kt plus ln r naught, and comparing this with the y is equal to mx plus c. So our graph is going to be log of r and time t. So this is the intercept. Here the intercept will be log of r naught. Slope is again minus negative. Slope is going to be negative here in case of first order as well. Okay. Then if we take this equation, which is we have written here, this equation, if we take this equation, to that equation, so if you are plotting graph, okay, here is this time t versus log of r naught by r. Okay, so this is the plot of log of r naught by r. So this graph will be like this, with the slope we get k by 2.303. Okay, just by altering the equation. Okay. So from the equation that k is equal to 2.303 by t log of r naught by r. So from that it is clear that the plot of r naught by r against t is a straight line with the slope k is equal to slope k by 2.303. So that is the slope which we are going to get. Okay, so that is about integrated rate equation of for first order the integrated rate equation. Okay, so that is very important. Clear agidya? Okay, so integrated rate equation for zero order reaction and integrated rate equation for first order reaction, these two. So ಎರಡು ಕೂಡ 3 ಇಂದ 4 marks ಗೆ ಕೇಳುವಂತಹ questions ಇದಾವೆ with the graphical representation. Sometimes they may ask graph, sometimes they will not ask, but graph will be more valued during the competitive class exams. Okay, so then next we have is half life of a reaction. Half life of a reaction. So half-life of a reaction can be defined as the time in which concentration of the reactant is reduced to half of its initial value. So here concentration of reaction reduced to half of its initial concentration. So ಇದನ್ನ ನಾವು T off ಅಂತ denote ಮಾಡ್ತೀವಿ. Will be denoted as T off. Okay. So here also we have to derive half order equations for our expression for zero order and for first order. So for first zero order we'll take expression for half-life of a zero order reaction. Okay, here I'll write expression for half-life of a zero order reaction. So what we are going to do is we are going to take zero order reaction equation, that is K is equal to, just now we derived R naught minus R whole thing divided by T. So here T is going to be T off. Okay, then R will be equal to R naught by 2. R naught by 2, because here they have said that concentration of the reaction is reduced to half of its initial concentration. So therefore this is the concentration of reaction which is reduced to half of its initial concentration. Okay, so therefore K is equal to, we can write it as R naught minus R naught by 2 whole thing divided by T off. So therefore taking LCM here, K will be equal to 2 R naught minus R naught by 2 T off. 2 T off. So here this. Okay. So therefore K will be equal to, from this next, K will be equal to K is equal to R naught by 2 T off. Okay. So now T off is equal to R naught by 2K. So this is the equation for zero order reaction. So here if you observe, T off is directly proportional to initial concentration. Okay, that is half-life period of the zero order reaction is directly proportional to the initial concentration of the reactant. So initial concentration directly proportional agide T off ಗೆ. So it is very important. Okay, so this is expression or derivation for the expression of half-life of zero order reaction. Similarly, we have to do this for first order reaction. Okay. So next for first order reaction expression. half-life of first order reaction. Again, we'll take an equation here, that is K is equal to 2.303 T into log of R naught by R. Therefore, again it will be T is equal to T of, and R will be equal to R naught by 2. Substituting that here, K is equal to 2.303 by T of into log of R naught by 2. So R naught by 2. So here R naught gets cancelled, and K is equal to 2.303 T of into log 2. So therefore T of is equal to 2.303 into log 0 is 0.3010, whole thing divided by T of, sorry, K. So this is K. So therefore T of is equal to, we multiply that to, we'll get 0.693 by K. So this is the expression for half-life of a first order reaction, and it is very important. Okay. So here we observe there is no R naught in the equation. In the final equation, there is no R naught, which means there is no initial concentration. Therefore, we can say that half-life of a first order reaction is independent of initial concentration. Okay, so that is what we can say from the above equation. So that equation is very important. So we will be having numericals also on that equation. Okay, so the half-life first order reaction is independent of initial concentration of the reactants. Is that clear? Okay. So this is about integrated rate equations of zero order and